Thank you very much for joining me for this lunchtime seminar with the Energy Futures Lab. I'm going to give a bit of a high-level overview of some of the work that we're doing in my group at the moment. So apologies to those of you that are more expert in wind turbines, but it's going to start off with a high-level introduction. So the first thing we need to discuss is how do wind turbines work? Well, essentially the blades of a wind turbine are aerofoils and therefore produce lift. This lift obviously sets in motion some kind of axle, and this induces a torque on an electromechanical generator, and ultimately that leads to the generation of electricity, which is sent onto the grid. However, they also produce a wake. Okay, now a wake in this sense is similar to something you might see behind a boat or a bus or something like this. And essentially, it's a region of reduced velocity with respect to the flow going past the wind turbine. This is because, of course, a wind turbine is harnessing energy, and therefore there is going to be an energy and a momentum deficit downstream of the wake. I should refer to this as a velocity deficit. That's the difference between, let's say, the free stream velocity and the velocity within the wake itself. Now, because wind turbines, and in particular modern wind turbines are very, very large, the Reynolds number for this flow is very, very high, and accordingly, these wakes are turbulent. And this introduces some problems, of course, because if we look at a wind farm, we can see that centrally located turbines within the wind farm are situated within the wake of the upstream turbine itself. So in a sort of one-dimensional schematic, we have something like this, where the first row of turbines produce wakes, which are incident on the second row. We then got the combined wake of the first and the second rows, which are incident on the third row, and so on and so forth. And of course, this therefore has consequences for the performance of the wind farm itself. So we've said that wakes are regions of reduced momentum. And so this obviously translates to essentially a reduction in the amount of power that a turbine can harness when it's situated within the wake of an upstream turbine. So simply, we can show that in a sort of back of the envelope fashion, the power produced by a turbine is going to scale with the velocity cubed. Now, for those of you that have studied some sort of aerodynamics, you'll know that we can obtain a force, an aerodynamic force such as drag, by taking a dimensionless drag coefficient, multiplying it by the dynamic pressure, which has got a velocity squared term in it, and multiplied by a reference area. Now, of course, a power is a force multiplied by a velocity, and so we can see that the power is going to scale with velocity cubed with some dimensionless power coefficient Cp in here. Now, this has pretty serious consequences for the operation of a wind turbine, because the fact that the power scales with velocity cubed means that a 20% reduction in incident wind speed might be expected to translate to something like a 49% reduction in the amount of power that we can harness. So these can build up pretty rapidly because of this cubic dependence. So actually, we've got some interaction for you. So there's no such thing as a free lunch in the Energy Futures Lab. So I've got a question for you here. I'm going to show you the importance of turbine spacing in a wind farm. And we've got two scenarios. I've got 7 wind turbines, relatively closely spaced, such that these turbines are exposed to a 20% velocity deficit. Or alternatively, I've got 5 turbines, and the spacing between these 5 turbines is larger, such that these turbines are only exposed to a 10% velocity deficit. So the question is, which of these two configurations generates more power? We'll take a vote. So who thinks that the 7 turbines are going to produce more power? Anyone? Who thinks that the 5 turbines will produce more power? Okay, everybody. Now, I'm afraid I've tricked you. So if we do the maths, we can see if I've got a 20% velocity deficit, then my power, I've got 6 turbines here, exposed to, let's say, something like 0.8 times the velocity cubed, plus I've got the first turbine, which is operating at 100% efficiency. So these 7 turbines are generating roughly the same amount of power that we might expect for 4 turbines operating in isolation. However, when the 5 turbine thing is here, we can see that 4 of them are operating at 90% efficiency, plus the first one is operating at 100% efficiency. This generates just under 4 times the amount of power of one individual turbine. So you all got it wrong, I'm afraid. However, yes, Rafa. Exactly. I was just about to say, which one would you build and which one would you operate? The correct answer is you would build the second farm because A, the capital costs are lower. I only have to buy 5 turbines rather than 7 turbines. And B, I might expect there to be additional maintenance costs associated with the 2 additional turbines. So the rational decision would, of course, be to buy and build the bottom farm rather than the top farm. Now, we mentioned that the wakes are turbulent. So not only is there a velocity deficit, but the flow is also turbulent. And that means that we have velocity fluctuations in 3 dimensions. So I might have velocity fluctuation in the streamwise direction, a velocity fluctuation in the vertical direction, and a velocity fluctuation in the spanwise direction. Now, what is the consequence of this on the blades of the turbine itself? Well, let's just imagine I've got a wind speed of u infinity, which is traveling in this direction, and I superimpose on this a velocity fluctuation v prime, such that the incident vector on my blade looks something like vector v here. Okay. Now, again, for those of you that have ever studied aerodynamics, we know that for an aerofoil, the lift coefficient, which is effectively the dimensionless lift that the aerofoil produces, is a function of the angle of attack, where angle of attack is this quantity here, alpha. And so in this particular scenario, I'm going to be generating this amount of lift. However, if I have an enhanced velocity fluctuation, I'm going to produce slightly more lift because I'm going to move along the lift curve slope. Conversely, if my velocity fluctuation is diminished, I'm going to move down the lift curve slope to produce a smaller amount of lift. And indeed, I could even have a very large velocity fluctuation such that I'm producing no lift, or almost possible we could produce negative lift in a very strong fluctuation. So the point is that the presence of the turbulence within these wakes is also significant because it's going to lead to fluctuating loads on the blades themselves. And so fluctuating loads on the blades themselves has consequences when it comes to extracting useful power from a wind farm. Because, of course, if I have fluctuating loads on the blades, that means I'm going to be producing a fluctuating amount of power. And this is, of course, relatively useless if I need a consistent amount of power in my factory to build more wind turbines, whatever it might be. Similarly, when my components are exposed to fluctuating loads, this can accelerate the process of fatigue damage. So fatigue damage, which is illustrated here, is essentially when I have cyclic loading. Eventually, my components might fail due to this fatigue mechanism. And indeed, fatigue failure is really important on wind turbines. Particularly vulnerable components are going to be the trailing edge bond on the blades themselves. And we can see particularly in the root of the blade, because in the root of the blade, we have the highest bending moment because we get the accumulation of essentially all the bending stress in the blade. We can see failures. And another key point of failure through fatigue is the gearbox. So fatigue damage is accelerated by virtue of the fact that turbines are exposed to these turbulent inflows. And then finally, of course, if I've got fluctuating loads on the turbines, I'm not going to be producing as much power as I might if I had a nice consistent uniform flow and I was able to design my turbines to operate in absolutely on design conditions. So we reduce the overall power that this wind farm can produce. And so turbulent wakes really are problematic in the context of wind farms. So if we want to essentially deal with the fact that we have these turbulent wakes, we need to somehow understand them such that we can accommodate for the fact that these turbulent wakes exist when we design future wind farms. So in some sense, what the work that we're doing in my group is about is we're trying to develop the tools to optimize the layout of future wind farms, accounting for these negative consequences which arise from turbulent wakes. So in order to optimize the layout of a wind farm, naively from a purely aerodynamic perspective, I would argue that we need to come up with some sort of merit function where this merit function rewards the overall power that we produce from the farm, but by the same token, it also penalises expected maintenance or replacement of components that have been damaged through fatigue cycle. So the merit function requires both a consideration of power produced and also the negative consequences from fluctuating loads such as fatigue. And this therefore requires us to predict the nature of the turbulent wakes that are produced by wind turbines. And so essentially the overview of what we're doing is given in this picture here. So here is a wind farm, and we can see I've got the front row of turbines. In this case, this is a wind farm off the coast of Denmark. These are 2 megawatt turbines. And typically we might expect these central turbines, which are situated in the wake of the upstream one, to be operating at around 55% efficiency, something like this. So whilst this one might be producing 2 megawatts, we might be expecting this one to produce as little as 1.1 megawatts of power. Additionally, these are exposed to highly unsteady loads, and therefore they're susceptible to fatigue damage. So somehow we need to try and map the turbulent inflow to the mechanical response of the turbines, such that we can get an understanding of what is the likely fatigue lifetime for the components on this wind turbine with regards to a wind turbine which is operating in isolation. And the way that we're going to do that is essentially we're going to look at 4 different things. So one, we're going to look at the mechanical response of the turbine components to turbulent inflow. But we need to, in order to do that, we need to predict how do these turbulent wakes spread and what are going to be the conditions that this turbine is exposed to. So obviously we need to better understand and model the turbulent wakes to do that. Now, the first thing we're going to be looking at is the near wake physics, because simple wake models, obviously we need the wake model to be simple, because if we're going to run optimization, it has to be cheap, because we're going to have to evaluate the merit function many, many times. And the problem is that the near wake physics are very flow specific. They depend on the design of the turbine. They contain all kinds of unpleasant coherent motions. So they're very, very difficult flow physics going on in the near wake. We need to have a better understanding of this so that we can propagate the far wake model. And the far wake model, essentially what we're concerned about is how rapidly do these wakes spread? Okay, so we know that wakes spread, but the rate at which they spread is determined by the rate at which background fluid is transported and mixed into these wakes. And this process is what's known as entrainment. So we also need to have a better understanding of how is fluid entrained into this wake and this wake spreads. And then finally, we also need to consider what's called the global blockage problem. I won't be going into this in today's lecture. This is ongoing work that's just been started with Adrian. So there's only going to be a couple of slides on that at the very end. Okay, so first of all, let's consider the near wake physics. Now, wind turbine blades shed coherence into the wake, and this coherence can originate from many different locations. Probably the most classical example that people think of is essentially the blade tip vortex. And this exists because essentially we've got circulation around the wind turbine blades, and this circulation has to be shed somewhere. And so we have this sort of classical picture of a helicoidal tip vortex, which is shed into the wake. However, this is an overly simplistic picture of what's going on, because not only do we have shedding from the blades, we also have shedding from, for example, the tower and also the nacelle and other components on the wind turbine. Now, the tower and the nacelle are bluff bodies, and bluff bodies have a typical shedding frequency associated to them. And this depends on the flow speed and also the diameter of the component. So we might expect the tower, which is obviously very wide, to be shedding at a different frequency to the nacelle, which is relatively speaking narrower. And of course, this is also a function of Reynolds number as well. Now, in general, the shedding of these things is a function of speed and size of the object. In general, big and slow, which is low frequency, and this is the example of the vortex shedding downstream of a volcanic island in the ocean. So this you can see is length scales of order kilometers, and therefore time scales of order multiples of seconds. Whereas for something which is relatively small, then we have a relatively high shedding frequency. And so again, we might expect there to be different frequencies associated to the tower and the nacelle. And here is a nice illustration of some numerical work which was published a few years ago, where they simulated wind turbines both without and with a nacelle, and they showed that the dynamic response of the wake was fundamentally different when they did and didn't include the nacelle. So in addition to having all of these different frequencies present in the flow, somehow they interact with each other in a likely non-linear fashion in order to determine the sort of large-scale dynamics of the wake itself. So some of the things that we're going to be interested in, so we're going to be interested in, let's say, the tip vortex, and this is beautifully illustrated through a lightning strike of a wind turbine, I believe, in Texas. So we've got the tip vortices, we've also got some shedding associated to the nacelle, there might be some vortex shedding associated to the tower, and then if we go sufficiently far downstream, as I say, all of these things kind of interact with one another, and we produce a very large scale but slow meandering motion associated to the wake. And of course, this is quite damaging from a loads perspective, because if the wake is meandering like this, for example, such that one blade of the turbine is cutting through the wake, but another blade is not, then we have a very asymmetric loading case on the turbine itself. So we were also interested in trying to understand the origin of this wake meandering as well. So the first sort of tranche of work, really, we've done some experiments in the hydrodynamics laboratory in the aeronautics department. So you can see we've got a model of a wind turbine like this. It's submerged in our water facility, water not pictured in this particular experiment, in this particular picture, of course. And then we do some cool experiments with lasers where we are able to extract the velocity field using a technique known as particle image velocimetry. Okay, I won't go into the details of this now, but if you have any questions, I'm happy to speak about those afterwards. And the important thing is we're able to capture these images reasonably quickly. So this is one of the motivating factors for doing the experiments in water, is that we can effectively slow everything down, and we can get a pretty nice picture of what's going on in the near wake of our model wind turbine. We can see things like blade tip vortices. These tip vortices then start to merge as we move a bit further downstream. We can see shedding originating in the vicinity of the nacelle. We can see the asymmetry introduced by the tower. So we can capture all these kinds of interesting things that are of interest to us. And if we look at the mean velocity profiles, we can identify various inflection points, and inflection points are associated with the introduction of coherent motions. And so we can see inflection points associated with the nacelle, the blade, and the tip vortices. Now, the picture is more complicated than simply looking at just the blades, the nacelles, and the tower. What we've got here is we've got spectra. So this is effectively frequency on the x-axis and magnitude on the y-axis. And if we capture spectra at this location, we can see that the dominant frequency is FR, and FR in this context is the rotor frequency. Whereas if I look at the spectra at this location, I can see that the dominant frequency here is 3FR. Now, of course, my wind turbine has 3 blades, and so 3FR corresponds to the blade passing frequency. So somehow the coherent motion in this region, we can see through this vortex merging process, leads to a much reduced contribution from the blade passing frequency. We can see that 3FR is diminished to quite a small amount, but we built up energy in FR with respect to this thing. So there's clearly interaction going on between the various coherent modes that exist in this wind turbine wake. Now, if I take a view from the top and I look at the spectrum at this location here, which is quite close to the nacelle, I can see a spike in the spectrum corresponding to the nacelle frequency. But if I go a bit further downstream to this location here, I can see that this has shifted to a much lower frequency. And so essentially what's going on as I move in the downstream direction is we get this interaction between the various coherent modes. And what we're identifying at this location is, in fact, the wake meandering frequency. So that very large but slow meandering that I talked about previously. And if I now take a look on this cut, which doesn't intersect the nacelle, but instead intersects the tower, I can see, again, I've got a new frequency here, which is associated to the shedding of the tower. And you can even see that with your naked eyes, I think. Whereas as I go further downstream, I don't really see any distinctive spikes in the spectrum. So essentially, this gives us some indication that the wake meandering somehow seems to be seeded by the presence of this nacelle. Okay, so this is something that we're working on. the influence of the nacelle wake exceeding the wake meandering. Okay, so we can paint a picture now of essentially what we call the sort of dominant frequencies in the different locations of the wake. And so each of these different sort of colours corresponds to a region of the flow where I've got one particularly dominant frequency. So this dark red region here corresponds to where the blade passing frequency is dominant. This yellow region here is where the rotor frequency is dominant. And then this kind of lighter coloured region here, we can see the wake meandering frequency is dominant. Now, if you compare these two pictures, I think the important thing to note is that these two pictures are fundamentally different. And this corresponds to a tip speed ratio of 4.5. So the tip speed ratio is effectively the ratio of the speed of the blade tip due to the solid body rotation and the oncoming wind velocity. And so we can see that the nature of the coherence in the wake is a very strong function of the tip speed ratio. Of note, we can see in the blade tip region, we have a two-step vortex merging process at tip speed ratio 4.5, where we go from 3FR to 2FR and then finally to FR. Whereas in the tip speed ratio of 6, we only have a one-step vortex merging process, okay? Because the turbine is rotating more quickly, the tip vortices tend to merge in one location and we go straight to FR. So again, it goes to show the complexity of understanding the near wake and the importance of things like the operating condition of the turbine. We can also see this is essentially the vortex shedding from the tower. We can see that the tower actually has quite a substantial effect on the flow itself because the tower introduces a very large asymmetry. So clearly the underside of the flow here is exposed to the tower, whereas the top side here, there is no exposure to the tower. And this leads to an obliqueness in the near wake, in which we see essentially a motion induced downwards in this sense on the lower half of the turbine and more upwards in the top sense of the turbine, which introduces quite a strong asymmetry. And these are results that come from some numerical simulations where you can see the presence of the tower does really introduce strong asymmetry in the flow. So again, this is complexity we have to deal with in our modelling approach. So because we've identified the nacelle as being an important contributor to the overall dynamics, we're currently doing some experiments where we're trying to suppress, shall we say, the vortex shedding that comes from the nacelle. So we can try and make the nacelle aerodynamic. So this shape is something you might see on an Olympic cyclist, for example, where they have an aerodynamic type helmet. The idea being to try and reduce the vortex shedding induced by the nacelle and therefore the effect that this has further downstream, where we get this kind of merger between the tip region, let's say, and the nacelle region, the tower region, to lead to the sort of large-scale wake meandering. So again, this is ongoing work at the moment. And then finally, we might be interested in the physics. So why do these different coherent motions exist? What are the energy sources that energize them? And so we developed what we call the multi-scale triple decomposition. So this is where we take the velocity and we're able to decompose it into a mean velocity plus a fluctuation. But the fluctuation itself can be decomposed into what we call a stochastic part. So this is effectively the turbulence that exists within the flow, plus a sum of the various coherent modes that exist within the flow. So for example, we might have the rotor frequency FR, we might have the blade passing frequency 3FR, we might have the nacelle shedding frequency, the tower shedding frequency, etc. And what we can do is we can use this multi-scale triple decomposition in order to derive energy budgets, and these energy budgets can track the exchanges of energy between these various coherent modes, so we can try and identify what is responsible for energizing these particular motions. So this is what the energy budget looks like for the coherent kinetic energy. So this is the kinetic energy contained in those coherent motions. We've got various source terms on the right-hand side. So there's convection. So essentially, if I consider a particular region of space, then convection is essentially what is brought into this region of space minus what is advected out. I've got production of this coherent energy, and this is production in which energy is transferred from the mean flow into the coherent motion. I've got production of stochastic kinetic energy. So this is effectively where energy is transferred from the coherent motions into the turbulence, basically. And so you can see this has a negative sign and is therefore a sink, in the sense that energy is lost from the coherent motion and instead is transferred into the stochastic motion. We've got direct dissipation and diffusion, but we expect both of these to be small when considering the coherent motions, because dissipation usually occurs at the smaller scales in the flow, and so is usually associated with the stochastic motion. But we also have these new terms which we identified, which we call the triadic production terms, and these are effectively exchanges of energy between various coherent modes. So, for example, if I have three modes like FL, FT, and FS, this could be, for example, the blade passing frequency, this could be the rotor frequency, and this could be, for example, 2FR. So long as these three frequencies sum to 0, I might expect there to be some transfer of energy between them. And this, of course, arises from the nonlinearity in the governing equations for fluid mechanics. So let's try and identify where these various coherent modes come from. And actually what we can see is that the rotor frequency is primarily energized, that's what this blue bar here is, by production. So effectively the rotor frequency, the energy source is the mean flow. The blade passing frequency is primarily energized through convection. So if I'm considering a field of view like this, the blades are passing around like that. Essentially the energy is convected into my field of view. Whereas things like 2FR, you can see, are energized by this triadic production term. So essentially, this is the result of nonlinearity existing within the flow, and we've got a transfer of energy from one coherent mode to the other. And this is the same experiment, just showing repeatability. But importantly, if we look at the wake meandering is largely energized by production from the mean flow, which is suggestive of the fact that this is a global instability mode, which needs a bit of a kick from the nacelle, as we talked about, in order to set it off. So that's one of the reasons why we're looking at making aerodynamic nacelle shapes, to try and essentially not give it that kick, which is going to be necessary to energize the wake meandering. Okay, so that's essentially the sort of near wake physics. Now, point number 2, like I say, we need to be able to try and predict how do these wakes spread. And the process through which wakes spread is known as entrainment. And essentially, if we want to come up with a simple wake model, so let's say I want to say that my wake is going to spread like this, I might say that the wake width delta is going to scale with distance x. And the simplest thing I can do is I can say this is going to be some sort of power law. And the simplest power law is I can set A is equal to 1, which means I've got a linear spreading. And indeed, linear spreading is what is used by the majority of the industrially used wake models. However, this power law in general is going to be dependent on the rate at which mass is transferred from the background into the wake itself. It doesn't necessarily just have to be mass, it can be momentum as well. So, for example, most of these simple wake models are based on simple conservation laws, things like preservation of mass or preservation of mass and momentum. So obviously the rate at which mass and momentum are exchanged between the background and the wake are going to be important. Now, we know that all turbulent flows grow with streamwise distance, and this is because of entrainment. And entrainment is also an important phenomenon in cloud microphysics as well, for example. But how do we go about measuring this entrainment rate, and what is entrainment rate? Well, let's take the simplest possible turbulent flow. Let's imagine I've got a turbulent flow which is growing in a non-turbulent background. In these circumstances, the turbulent flow contains vorticity, whereas the background does not, and therefore the outermost boundary, or the interface between the turbulent flow and the background, is simply going to be an isosurface of 0 vorticity magnitude. And so we can therefore identify this boundary by simply placing a vanishingly small threshold on vorticity. And of course, identifying this boundary is going to be crucial if we want to measure the entrainment flux across it and therefore apply that to the spreading of turbine wakes. However, the situation for wind turbines, and indeed volcanoes and clouds, is complicated by the fact that they don't spread into a non-turbulent background. The atmospheric boundary layer is itself turbulent, meaning that I have vorticity in the background as well as vorticity within the primary flow itself that is spreading. So I can't simply rely on identifying this interface by using a vanishingly small threshold on vorticity magnitude. So we need to come up with an alternative way of doing that. And indeed, we can see actually this is quite a nice illustration. I think you can see that this particular portion of the interface of the volcanic plume is probably being generated by a sort of vortex in the atmospheric boundary. That's quite a nice illustration, I think. Nevertheless, how do we go about doing that? Well, we come up with a new experimental technique, which we call PLIF. Essentially, what we do is we seed scalar into the wake. And if we choose scalar, which doesn't diffuse very quickly, then essentially the scalar remains, to all intents and purposes, trapped in the wake. And so essentially we can take images of the wake where the background contains no scalar and the scalar is contained within the wake itself. And then, of course, what we can do is we can identify an interface separating the wake from the background. Now, here are two images. This is one where the background is non-turbulent, and this is an image where the background is turbulent. And I think you can see that the structure of this interface is fundamentally different in these two different scenarios. So it's really important that we try and capture the physics associated to background turbulence when it comes to wake spreading. Okay, so how do we go about measuring the entrainment? Well, first we identify the interface position at some time t. Then I look in the time series and I find the interface at the next time t0. What I can then do is I can then find the local fluid velocity along the interface. That's what these green arrows are here. And I can advect the interface backwards in time by the local fluid velocity. And if I do that, I can see that these two interfaces do not directly intersect on one another. And that's because I've entrained some fluid in the time period between my two images, delta t. And so essentially, if I identify the displacement between these two interfaces and divide through by time delta t, I get something called an entrainment velocity. And what I can do is I can integrate the entrainment velocity along the interface to see what the entrained mass flux is going to be. And what we did is we compared the length scale of the background turbulence to the intensity of the background turbulence to see which of these is going to be more important in determining the entrainment rate. And there's no correlation really between the length scale. And whilst this is a rather heroic line of best fit that my student put in, we can see that nevertheless there is a diminishing trend whereby entrainment mass flux actually decreases as the turbulence intensity of the background increases. So obviously it's important that we capture this, because if the background is more turbulent, my wake is going to be spreading at a slower rate than if the background is more turbulent, than the background is less turbulent. Now, all of those previous experiments were done in the far wake. So they were all done in, let's say, this region here, for example, some 40 diameters downstream. But of course, wind turbine spacing is usually of the order between 5 and 10 diameters in terms of spacing. So really, we need to know about the spatial evolution of how do these wakes spread from the beginning through to the end. And so if we just look at essentially the average location of the interface, and we plot that as a function of streamwise distance for the different cases of background turbulence we have, we can see that there seems to be a fundamentally one slope in the near wake and then a second slope in the far wake. And by and large, this seems to coincide with a location around 15 diameters, which captures the coherent motion within the wake. So again, wind turbines have got this coherent motion in the wake. So clearly these coherent modes are going to be important in determining the entrainment rate in a sort of practically useful distance. So what we've now done is we've now essentially measured the entrainment velocity as a function of the turbulence intensity of the background. And we can see that as I move downstream, so I'm going from 6.5 diameters all the way down to 40 diameters, I can see that the entrainment rate decreases. But I can also see that the rate of decrease of entrainment due to the presence of background turbulence is much more stark in the far wake. So here I've got essentially the closest approximation we have to a non-turbulent background. You can see there's a substantial reduction in entrainment at 40 diameters downstream, but this is less significant when I get to the near wake. So actually this is good news from a modelling perspective for wind turbine wakes, because really we're more interested in this region of the flow than we are in this region of the flow. But I said that not only do we need to worry about entrainment of mass, we also need to worry about entrainment of, for example, momentum and kinetic energy. And without getting involved into this sort of maths, if I consider entrainment from an idealized non-turbulent background, effectively there is a direct proportionality between the entrainment rate of momentum and the entrainment rate of mass. All I need to do is I say that if I know what the mass entrainment rate is, I multiply by the free stream velocity, and I've got the momentum entrainment rate. However, when I have a turbulent background, this is not the case, because I might, in general, have correlations that exist between the velocity fluctuations in the background and the entrainment velocity. And so if these correlations exist, then the direct proportionality between the entrainment rate of momentum and the entrainment rate of mass disappears. The same thing is also true for kinetic energy, where I've now got 3 different correlations which can effectively change the efficiency with which kinetic energy is entrained relative to mass when considering entrainment from a turbulent background. But we've measured this, and the good news is that essentially the efficiency is preserved. This is because the correlation between the velocity fluctuations and the entrainment velocity is relatively small. It only really seems to affect the entrainment of kinetic energy, and only in this near wake region. And that's because we've effectively got the sum of 3 small valued correlations as opposed to a single correlation. So this is indeed good news when it comes to modelling, because we can still use what's called the entrainment hypothesis. The entrainment hypothesis states that the mass flow that is entrained can be related to some velocity scale in the flow multiplied by something called the entrainment coefficient. This can then be used to multiply through by, let's say, velocity scale u0, and I can still use this entrainment hypothesis to model the entrainment of momentum. So this is actually a very good piece of news when it comes to modeling spreading in turbine wakes. Okay, so just some sort of interim conclusions here about entraining into wakes. Now, the third thing I want to cover is going to be the fluid structure interaction. So essentially, where I place the wind turbines is going to obviously depend on what my expected fatigue lifespan is going to be, as well as the amount of power that I'm going to produce. Because what we want to do is we want to avoid situations like this, where either the tower or the blades fail due to accumulated fatigue damage. Why is that not cycling? Okay, so what we've done is we've developed some novel experiments. So the first time what we've done is we've coupled a fiber optic device which is embedded into our flow. So this is representative of the tower of the wind turbine. And we've captured fluctuating strain simultaneously to the time resolved velocity field in the vicinity of the tower. So, for example, we've got various fields of view. So you can see this green field of view, it's in the sort of spanwise direction. And then we've taken various planes at different locations along the cylinder. And we capture that simultaneously to the fluctuating strain that is picked up by this distributed sensing network. And what we do is we expose the tower to different cases of free stream turbulence, where I can vary both the length scale and the intensity of the background turbulence to see how does this background turbulence map to fluctuating strain within the structure. So we're using what's called Rayleigh backscattering sensors. So essentially these fiber optics are embedded to the surface of the cylinder. If the fiber is exposed to a strain, then essentially as I fire a laser beam, I'm going to get a reflection. And this reflection is obviously going to be a function of how much this fiber is deformed. And that's going to give me an indication of what is the local strain. And the good thing about this is I can, by measuring the time taken from the emission of the beam to capturing the reflection, I can get a distributed strain. So essentially I can get the strain along the tower rather than just a localized thing like you might get with a strain gauge. And we instrumented the tower at 4 different locations, so plus or minus 45 degrees and plus or minus 135 degrees. And this gives you a bit of an indication of the type of data that we can collect. So here I've got the example where I've got no turbulence generating grids upstream. Here I've got one particular case of turbulence that's been generated. We can see this is what the velocity looks like in the wake in both of these cases. This is the fluctuating strain that we can capture along the various fibers. What we can also do is we can also do a modal decomposition onto the velocity field to try and identify what are the key coherent modes that exist within the flow. And what we can see is we've got the sort of planar vortex shedding, and we can see that the coherence of this vortex shedding is actually enhanced when I have background turbulence relative to not having background turbulence. And additionally, I've got tip vortices which originate from the free end of the cylinder as well. And all of these coherent modes contribute to the fluctuating strain that's going to be within the structure. So here what we've got is so this is no grid, this is with turbulence. You can see here's the mean strain, and here the green gives me the RMS and the blue gives the sort of min max variation. We can see a substantial enhancement of the fluctuating strain when free stream turbulence is present. And what we can do is we can then look at the spectrum of the fluctuating strain, and we can compare the spectrum of the fluctuating strain to the spectrum of the velocity field. And we can see I've got a strong contribution at the vortex shedding frequency, in particular in the root region, because of course this is where I get the accumulation of all the bending. But we can see that the contribution in this frequency band is much, much larger when I have free stream turbulence present than when I don't have free stream turbulence present. In addition, I can see a low frequency contribution, and this low frequency contribution seems to map quite well to essentially this region here, which is associated to the tip vortices that we mentioned previously. And we can also compute, let's say, co-power spectral densities, where I literally compute the correlation in spectral space between the fluctuating strain and the velocity field. And we can see how does this evolve as we move downstream. So effectively, there's no contribution upstream of the cylinder. So essentially, if I have some structure which is exposed to a turbulent inflow, we might think that there's two different effects that the fluctuating inflow can have on the strain. One is what we call the direct effect. So I've got turbulence. This turbulence impacts the structure, and that yields some fluctuating strain. Or we've got the indirect effect, which is effectively the free stream turbulence modifies the vortex shedding process, and therefore the vortex shedding process, as I get the kind of deflection like this, leads to a different strain associated within the structure. What this shows us is that the direct effect seems to be pretty negligible, whereas the indirect effect, so the presence of the free stream turbulence at modifying the flow physics within the wake, maps much, much better to the fluctuating strain that we measure. So essentially, the free stream turbulence modifies the vortex shedding process. This vortex shedding process then imprints itself in the deflection and ultimately bending strain within the structure itself. And very finally, I'm going to just give two slides. The final thing we're going to be looking at is the global blockage effect. So if it's a very, very windy day, but I go into a forest, I don't expect to have my hat blown off. That's because, of course, the forest itself presents a global blockage to the wind, which might divert over or around the forest. And of course, the same thing is true for a wind farm. Wind farms are sufficiently large that they present some sort of blockage to the oncoming wind, and therefore, even if I have the same number of turbines in my layout where I'm trying to optimize, the configuration of those turbines does make a difference because of this global blockage effect. Indeed, this failure to model this global blockage actually wiped $3 billion off the share price of Ørsted in 2019. This was timely because this was when I was writing my proposal. So that worked out very nicely. Thank you very much. So we're now working towards this goal. So this is going to be the subject of another PhD, which Adrian's going to be doing, where we're going to be trying to understand how does this global blockage affect the flow through the farm, and ultimately how can we then model it. And so I think that's pretty much my 45 minutes done. So a quick summary of what we're doing. Wind turbines produce wakes. These wakes shed circulation into, so the turbine sheds circulation into these wakes. This has consequences for the wind farm, where it reduces the power production and also makes the power production intermittent. It can also accelerate the process of fatigue damage. We need to try and understand and model these physics so that we can come up with tools to optimize the layout of wind farms, which means we need to understand the near wake physics. We also need to understand how do these wakes spread via the process of entrainment. Finally, I also need to know about the global blockage, because a particular layout of turbines is going to give me a particular blockage effect. Once we've packaged all of these three things up together, we can put them into an optimization tool such that hopefully we can spit out wind farms that have been optimized for future energy goals. So with that, thank you very much for listening, and I'll take any questions. Of course, yeah.
So the first one is about the turbulent entrainment.
Yeah.
So generally, wake models say or state that the more turbulence intensity we have in the inflow, the higher the rate of expansion of the wave.
Yeah.
The main reasoning behind being turbulence intensity in the inflow enhances wake mixing in the wake, so the wake spreads faster.
Yeah.
You are stating the opposite.
Actually, I didn't go through this subtlety. It's a very good question. So in the far wake, so this is at 40 diameters downstream, it's unequivocal that free stream turbulence diminishes entrainment rate. And the reason for this is, imagine if I have, let's say, imagine I have two wind turbines. I have a small wind turbine and I have a large wind turbine. Okay, which wake do you think is going to win out in terms of entraining? Probably the large wind turbine is going to entrain the fluid from the small wind turbine wake, because essentially it has the higher turbulence intensity, etc., etc., etc. So from the context of the small wake, my very turbulent background means there's going to be a net detrainment rather than a net entrainment. So unequivocally, this is what happens in the far wake. However, in the near wake, the picture is more complicated. Now, there are two mechanisms for entrainment. There's one which is a large-scale process. Essentially, I swallow a large amount of fluid. It's called engulfment. And then there's a small-scale process which is related to diffusion. Now, our results suggest that free stream turbulence enhances the large-scale process, but diminishes the small-scale process. And in the near wake, the large-scale process is important, which is why, as you can see, this is my non-turbulent flow. We can actually see an enhanced entrainment velocity relative to the non-turbulent background. So these wake models are correct in the sense that they consider only the near wake, but I think this picture is quite a nice representation. What happens in the near wake at some point is going to transition. And now, whether this is relevant to wind turbine spacing or not is to be determined, of course. But we need to make sure we capture this change in behaviour if we're going to start spacing them out in a sort of relatively large distance.
Thank you.
Yeah.
I'll go to my
of course
one, which I think is related. So again, from wake modeling, the definition of the distinction between near wake and far wake, okay, it depends from the turbine flow, turbine geometry, etc. But I say, correct me if I'm wrong, around 4 to 5 diameters. That's kind of the line we draw.
Something like this.
Far wake.
Yeah.
It is very, so usually the turbine spacing you mentioned between 5 and 10, so we can say that generally turbines are spaced or located in the far wake of others. Why do we need to investigate so much the near wake? I know it affects the far wake, but do we need to focus more on maybe the interface between near wake and far wake to get these values to model them? Or like, why do we need, on a control perspective, go that deep into the physics of the near wake?
This is also a good question. Let's assume, for sake of argument, our model is valid from the far wake onwards, right? And I've got this linear spreading rate, for example. Now, I'm going to start spreading from this location, and I even know what the slope of the spreading is going to be. However, what goes on in the near wake is like the boundary condition, right? Because if my near wake is this wide, then I can propagate my wake accurately like this. But if my near wake is only this wide, I can propagate the wake in the same fashion and I get two different results. So in some sense, the near wake is like the boundary condition for what goes on in the far wake. Now, my second answer to your question is wind turbines are getting bigger and bigger and bigger. So the sort of largest offshore turbines now have a diameter around 250 meters. Now, it's just simply not practical anymore to space turbines 5 to 10 diameters apart. Okay, a 10 diameter spacing is 2.5 kilometers. So increasingly, turbines are going to be more closely spaced in the context of diameters. So, we're going to see increasingly 3 to 4 diameter spacing, simply because even a 4 diameter spacing is 1 kilometer. And of course, within the first 4 diameters, we've got near wake effects. Yeah.
In the previous slide, you mentioned about there was an inverse cascade.
Yeah, sure. So if I look at this 2FR, Okay, 2FR is energized by the triadic production term. Now, the triadic production term is only non-zero if the three frequencies in my triad sum to 0. So, for example, to produce 2FR, I would need, let's say, FR and 3FR, and that could produce either 2FR or 4FR. Okay, these are essentially the outputs that I can get from interaction between FR and 3FR. So what I have is effectively, I have a transfer of energy from 3FR, which is high frequency, to a lower frequency mode at 2FR. So essentially, energy is going in the opposite direction to what we might expect in a sort of classical turbulent cascade, where we go from large scales, low frequencies, to small scales, high frequencies. Yeah.
Just a station.
Yeah, exactly. So for example, I mean, you can actually visualize it in the videos. Here, for example, you can see, look, I can clearly see the blade tip vortices. That's characteristic of 3FR. Eventually, you can see I end up with and there's some 3FR and some FR here. Ultimately, I then end up in this vortex merging process going to lower frequencies. Yeah, of course.
And you mentioned about entrainment. Do you think the effect of the heat vortices will be important?
Yeah, for sure. Yeah, for sure. So the tip vortices effectively they're promoting motion like this into the wake, basically. So when these vortices break down versus when they don't break down, does definitely affect the entrainment rate. So like I say, there's two mechanisms for entrainment. There's the large scale process, which is termed engulfment, and these tip vortices are going to be very important for that. Okay. Thank you very much for coming.